Alright, well, let's try this again and see if this second recording works and uploads better. This week, and this is for those of you that are new to a course with me, this is LiveScribe, and I like to use different media, different audio-visual techniques. Brainshark is a bit new for me, and I use that as an introduction, but I like to use LiveScribe a lot. I do it in person when I have some of my in-class lectures, as well as obviously it's a supplement to a lot of my distance learning courses as well. So many of you are already very familiar with this, and other of you, this might be new, but hopefully this is this little TiVo lecture, as I like to sometimes refer to it as, it will be potentially helpful. What I like to do really this semester in EPI is use LiveScribe occasionally to sort of take some of the concepts that we are learning about in a particular week and sort of reframing them, or giving a little bit of extra information, at least especially from a statistical point of view. I do tend to sort of bring us back to some of these estimates and how they fit in a bit from an analytic point of view, since that is really what I do. A lot of my day-to-day work is really doing analysis and research and design sort of work. And so part of it is presenting a little bit extra information that may or may not be within the chapter a little bit, but it is sort of that idea about reframing it or trying to help think of a way to sort of summarize it that might help clear up if there's any particular bits of information that's confusing. And one of the things I want to talk about with this week is I want to talk about a couple of important estimates that are very critical in health research. And this particular week, in week 3, we're sort of getting our feet wet a bit with this idea about prevalence and incidence. And in particular, what I want to sort of help us do is, our textbook describes and uses different terminology. Then we have a supplemental PDF of additional pieces of information from a Hebel and McCarter chapter in a book, just to sort of help as extra background reading. But one of the problems is the textbook and that scanned book uses different words for the same things or the same equations or point estimates. And unfortunately, even I myself, when I was taught through the public health department at GW, I was taught a separate different type of labels. But so I want to sort of recapture a little bit to see how they're all tied in depending on which pieces of information you read. But the first thing I want to do is to sort of highlight a very important thing that in health research, it's very common to have outcomes, or I should say, our dependent variables. I think most of us in this course you've either had 270, 271, or you've had me in biostats. So I refer to dependent variables a lot. But in health research, it's very common for these dependent variables or outcomes to be nominal. And what do I mean by nominal? Meaning, and it's not just, there's categories, but even more specific, they are nominal variables or dichotomous. So we have things like disease versus not disease. Or we're looking at, are they cured versus not cured, or disease versus cured. That's sort of dichotomous. We look a lot at survival rates. So we might say, are they survived, or is there a death? So that sort of two groups. And obviously a really big important one is this idea about exposed versus those that are not exposed, or exposed versus unexposure. So things are very much in health research, this sort of the outcomes that we're interested in measuring or estimating is one side or the other. So they're either disease or not disease. It's either there's no gray, there's no in between. You're either one or the other, and this is very, very common within health literature. You look at the any journal article, you'll see a lot of these sort of outcomes in there. There are other outcomes, of course, that can be on a continuous scale, but nominal outcomes are very critical. And there's a couple of things to keep in mind when we are dealing with nominal outcomes, and something I just sort of want to summarize from, it's sort of within the textbook. But I want to sort of summarize it here. There's two qualities about nominal health or nominal outcomes. And there's two potential, or in the way I think you think about it from a statistician's point of view, he or she is going to ask the question. There's two potential answers to this question about the nominal dependent variable. The question is going to be whether or not that nominal dependent variable is affected by time. So either the nominal variable is not affected by time, means that I watched everybody for the same length of time. And think about it, a lot of our health research has to deal with, longitudinal studies, or we're looking at something, we're looking at a group of individuals or a cohort across time. And if it's not affected by time, that means that we looked at all 1,000 individuals from time one all the way to, 10 years later, 2 years later, however long our time is at. So when it's not affected by time, it means that every single individual was followed for the same amount of time. We looked for the occurrence of that disease, or their survival, or their exposure, whatever the outcome is. We looked at it along the same amount of time. And so one potential quality of a nominal outcome is it could be not affected by time. The other potential quality, so it's either going to be affected, it's either going to not be affected by time, or it is going to be affected by time. And in order for us to define it or identify it as being affected by time, there's two important definitions, both of which have to be true in order for this to be affected by time. First of all, the longer I look, the more I find. Well, that's true in just about any kind of health outcome. We know that the longer our study, the more we're going to see. So that's clearly an important part of the definition. But the second part of this definition also must be true in order for us to define this outcome as being a nominal outcome or nominal dependent variable affected by time. The second important piece is I look longer at some people than others. Meaning that some folks maybe as soon as they get, one potential thing is if they get the disease, then I no longer follow them. But really the biggest example, or the best example of this second quality about a nominal dependent variable affected by time is clinical trials. A lot of times we're not able to enroll everybody all at the same time. And therefore, everybody's enrolled on day one, and we follow everybody for the same 10 years. A lot of times we're dealing with staggered admission. We keep enrolling people throughout the first 6 months, or maybe it's a full 12 months. We look for, enrolling X number of people. And one example could be that no matter when they're enrolled, we're still going to end 5 years later. So some of these folks get watched for the entire 5 years. Some of them only get followed for 4 years. And then to add another layer of looking longer at some people and others is this idea about people withdrawing. We lost a follow-up. They move out of the area. Washington, D.C. is a big area that's always changing. Lots of people coming in and going. We have a lot of military and government agencies. A lot of people come and go, and they get stationed in another location or in a different office on the other side of the country. So there's a potential just for loss of follow-up because people are moving away. Loss of follow-up because people don't want to participate, or that the study's asking them to do too many things and it's just getting to be too tiresome and they just choose to not continue. So here's a couple of things, again, typically happening within clinical trials, but can happen in other particular study designs. But this is one of the biggest pieces of that definition of being affected by time, is the fact that people are enrolled at different times, or we're losing them at different times for whatever reasons. Or maybe we lose them because of death, which is not the particular outcome we're looking at. We're looking at for some other disease, and they're affected by some other disease that we lose them. So this is sort of critical to think about some of these analyses and these measurements that we're talking about this particular week when we think about how do we measure the occurrence of disease. And we think about ways not only just identifying does the disease happen, yes or no, do they have the disease, yes or no, cured, yes or no, but also when we think about the impact of not following people all the time, when we start thinking about what happens when mortality or just potential morbidity of other creation, something that takes them out of our scope of watching them to see what happens over time. And so really some important estimates for us to think about. 3 ways to measure disease that I really want to sum up for us today. Oops, it would help if I spell. Those of you that are used to me in my statistics courses, when it comes to numbers, I'm totally all for it, but I start to lose it when I'm concentrating on spelling a word. So what I want to do is talk about some important measurements that are presented to us in the textbook and also in that supplemental reading. You don't have to read the additional Hebel and McCarter pages. But what I really want to help do is indicate these 3 important measures of disease and also help kind of potentially clear up any confusion because there's a lot of different terminologies being thrown around and how do they compare and how do they differ. So the first and most important one that we want to think about is our good old friend prevalence. And prevalence, I like to define prevalence as being the proportion of those subjects or people with the disease at a single point in time. Let me spell that out. And I especially want to underline this last little bit here, single point in time. Prevalence is often what we think about as a point estimate. It's as if we're coming along that continuum of time and we just take a little snapshot, click right there, in June of 2012. Look at that month and we're looking at, okay, here at this particular time I took a snapshot, now let me count up how many people have the disease. And that's my numerator. And then my denominator is the total number of people in that population at that same time, in that snapshot. So when we think about prevalence, it's a proportion. I sometimes like to abbreviate it just as PREV, or sometimes you'll see it abbreviated just simply with a capital P. But I do like to at least spell out the first few letters of it. But it's the number of people with the disease at that time, and it's divided by the total number of people in the population at that time. So again, think about the fact that there goes time across, and I click take a picture, and I look at, in fact, I'm almost going to create a Venn diagram for those of you that have had my biostatistics class. Imagine that this is our little Polaroid shot, a little picture. And what I want to do is I'm looking at the snapshot, and I'm not sure if I've ever done it with stick figures, but I'm very visual, and I like to sort of think of ways to describe these things. And what I'm going to do is I'm going to, for those that have the disease, I'm going to fill them in, darken them up here. So Snap took a picture, and again, I say population. Obviously, you know, for those of you that know, I like to think about the population is not something we can actually attain everybody, but at least, you know, we can draw a large sample and ask them some surveys, and we find out who has the disease and who doesn't. So here, a snapshot is a picture of all of our people within our population. And let's say that in this example, despite the fact that I couldn't fit them all in the frame, let's say my total population, N, is equal to 100 individuals. And let's say that the particular disease I'm looking at I'm looking at who has a disease and who doesn't. I'm going to look at skin cancer. Either form, whether it's melanoma or the squamous cell. And I see within my snapshot 10 individuals that have that disease. So really what I can do is I can calculate prevalence as being A over N. Right? If, again, I wrote it up here with words, the number of people with the disease at the time, that's my letter A. My snapshot, click, 10 individuals had the disease, divided by the total number of people in the population at that same time that I took that picture. And I had 100 individuals that I was observing. 10 of them had the disease out of 100 individuals that I was looking at. And I have the prevalence of 0.10. This is sometimes reported as the proportion of 0.10, or you could say 10%. So 10% of the population had skin cancer. Or sometimes you can also report it as 10 per 100. Again, different ways that it gets reported. So prevalence, that's pretty much, the good thing is, regardless of where you're reading, prevalence is pretty standard. There's no different labels for it. It's always referred to as prevalence. Where we have a problem is when we start getting to the other two estimates or measures that I wanted to talk about. Now, as I sort of set up the next page, what I want to sort of remind ourselves here is that prevalence, I could take a snapshot at any different time, at any point in time. Let's say my study started in January 2010. I took, and I knew that, by June, I had several folks enrolled. I could take a snapshot and say, okay, here's now, by about June of 2012, I was starting to take some measurements. And so here's time 1. Click June 2012. Take the picture, count up the individuals, and divide it by the total number of people observed. And by then, I had only 100. I wasn't going to change, but I was going to then follow those 100 individuals for the rest of the time. So maybe I decide to take another snapshot a year later. It could be a 5-year study, and maybe once a year I take a snapshot, click, and I count up. Out of my same 100 individuals, I can certainly report it and say, okay, now out of those same 100, I still have the same 10 individuals that have the disease, but now I have another 5 individuals. So now I have 15. So then I can do a prevalence at any point in time. I did the June 2012, then maybe I do it again in June 2013. And I count up how many people out of my 100, still my denominator, how many out of those 100 now have the disease. Now maybe I have 15. 15 out of 100. It's the original 10 that I had in June of 2012, and now I take a picture and click, now I have 15 total. So point prevalences, or prevalence, can be any particular point in time. So you could think about having a prevalence at time 0, and then a prevalence at time 1 year, or 5 years, or 10 years, depending on how long the study is. So that's great. So I could take different point estimates, prevalence at different time periods. But sometimes I'm curious to think about, well, how about, what's the proportion of subjects who develop the disease over a period of time? How many people are at risk? And this is where we start getting, unfortunately, a little bit of variations in labels. Our textbook refers to it as attack rate. The Hebel and McCarter book refers to it as incidence rate. I know it as, or what, if I were to spell correctly, simple word is also known as risk. And I think it's a little easier to think about because we are talking about looking at those people who are at risk. They didn't have the disease when I started, but they're at risk of developing it. And I want to look at this idea about the proportion who develop the disease. Again, using the word rate, whether you say it's an attack rate or you call it an incident rate, it's still, in a lot of people like to use the word rate synonymous with proportion still, even though it's technically not a rate because we don't have time in there exactly. But the idea is I'm looking at those people who are at risk, those people who develop the disease. And let's talk about this a little bit more. Now I want to define this, and I'm going to stick with these terms. I'm going to kind of stick with this idea about risk. Despite, again, just because there's different labels. The textbook says attack rate. The other supplemental reading says incidence rate. It's basically we're looking at those people who are at risk. And I think that's why it's nicer to think of this idea about risk. Because they're the ones, and you'll understand why these terminologies of attack rate and incidence rate get used a lot too. We're looking at those individuals who don't have the disease, and we're looking at to see who develops it over time, who gets attacked, what are the new cases that are coming up. And I'll sort of come back to this name in a moment. I start talking and forget that I need to start writing as well. So let me define this risk. And And I'm going to define it as the proportion of subjects or people who develop the disease over a period of time. So this is important because we're talking about those who are developing the disease. Notice we're also starting to get this feel of time involved. It's not quite like prevalence where we just took a snapshot. Instead, almost think about it as we're lining up. Maybe we have our snapshot on, here's our June, our June 2012 snapshot with all the little pictures in it. And now we're lining it up and comparing it to a snapshot that we then take on June 2013. So here was June 2012. And now I'm looking at these pictures side by side. And I say, okay, now what I want to do is I want to start with this first picture. And I understand that there were 10 individuals that had the disease. But what happens if I want to look at the other 90 individuals who didn't get the disease? And I want to see, out of those 90 people in that picture from 2012, how many of them now have the disease in 2013. So, what I have now is, here's at time equal to 0. What I had is, we had 100 individuals, and I had 10 folks with skin cancer. Remember that the disease is still going to be equal to skin cancer. And now in the second snapshot, at 1 year, I have the same 100 individuals. I still have these old cases. That's equal to 10. But now I also discovered, I want to sort of remember that there were 10 individuals over there in the first picture. But now in my snapshot of June 13th, I see those same 10 people, but now I also see 5 new cases. So now at time 1, A is equal to 15. We call these old cases, we call them quote-unquote prevalent cases. Why they can't use some different words so that we don't get ourselves confused. This is not prevalence, but they're called prevalent cases. Meaning they're the old cases. And here's where this is why this risk gets called incidence rate. It's the fact that these new cases get referred to as being incident cases. And I think that's why it becomes a bit fuzzy or gray, or when you start trying to figure out, well, why are they calling it this and this other, you read it somewhere else in a journal article and you're thinking, what are they really calculating? So it's important to look at how they're defining it to know, are they really talking about risk? Are they talking about prevalence, or so on? So here's our little snapshot. Just from this situation alone, what I want to sort of remind ourselves is that I took 2 different snapshots, so I could take a prevalence at time 0. Remember, it's the A over N, so it could be the 10 over 100. I could also talk about because remember, prevalence is a point estimate. So I could also talk about at that particular time on June 2013, I had 15 over 100. I'm making the math much easier for me on this end. So now that I have two pictures side by side, I can talk about a point estimate of prevalence at time 0. And then I can also talk about prevalence within the second picture at time equal to 1 year. Now let's talk about this idea about risk, or sometimes referred to as incidence rate or attack rate. Now I'm just going to keep labeling it as risk. Risk is going to be defined, if we look up at our verbal definition, it's the proportion of individuals who are at risk So it's the number of individuals who develop the disease. And the denominator in this, remember that we're thinking about the people who are at risk, so it's the total number of people who are disease-free at the beginning of these two snapshots. So I like to think of it as it's to the total number of people who are disease-free at the start of the time period. So now for this idea about risk, looking at our example, we had a total of 90 people. At that time, at June 2012, we had 100 individuals. 10 of them had the disease. That meant the other 90 were disease-free at that time. So they were the ones that were at risk of developing it. They were the ones that were at risk of being attacked. Thus, we get this idea about attack rate. They're the ones that are at risk of being incident cases. So if you want to use the label of incidence rate. Again, all three of these labels, really it's talking about looking at this proportion who are at risk. The proportion of developing the disease. So now we had 5 individuals, 5 incident cases. That's where our incident cases plug into, is up in the numerator when we calculate this risk. And what I get is 0.0, well, I want to keep it to just 2 decimal places. So I get 0.06, or, again, it could be 6%. Or you can also talk about 6 per 100 are at risk of developing skin cancer. I mean, I'm just using various numbers. It's not necessarily a great example of exactly the rate. But it's interesting, it's also important to note that what this risk is, this is the risk or attack rate or incidence rate over a 1-year period of time. I could potentially have this going out for 5 years. And I could do, if I wanted to measure it every 1 year, but maybe it's 5 years later, and maybe instead of 5 out of 90, I took the snapshot and 90 were disease-free, and 5 years later, maybe I have 20 new incident cases. So then it becomes 20 over 90. So it's however long that time period, that delta, that change in time, is reflected on whatever type of risk or attack rate that you want to establish. So what I want to kind of close out with is our third measurement. And our textbook talks, actually I really like the Hebel-McCarter diagram they have some pictures about like a flask. And it's very similar. I use a slightly different picture. And what I want to do is sort of, I'll start off with that, and then let's talk about our third measurement. And let me just bump up the numbers just to help a little bit of our numbers. I like to think of it, my advisor at GW University used this, and he and I have often laughed about how, or talked about how this is very helpful when we think about how these different estimates are similar and how they are different. Think about a spigot that's alongside a building, and right beside or right underneath that spigot is this large barrel. And I can turn on that spigot. This is my best. I'm much better at stick figures, obviously. But I can turn on that spigot and, dump water into there, close off the tap, whatever. And let me just sort of point out where these different estimates or different examples come into. So let's say we take that snapshot on June 2012. Another way to think about it is, okay, where is that line? Where does the water, how high up is that water in that barrel at the time? And this would represent, there's that prevalence at time equals to 0, right? So that would tell us, this prevalence estimate at this particular time tells us what's the proportion of people with the disease. Now let's say I want to change it up just a little bit. Let's say we take another measurement, and instead now it is 5 years later. I want us to lead us into this third measurement, give us a little bit more time than just 1 year. Now let's say it's June 2017. We've all graduated from GW University. We're doing research. I again, now notice what I've done now is I've drawn another line on that barrel. So now over the 5 years in time, the water has risen up to this next level. And what that next level reflects is the prevalence of the disease at time equals to 5 years. At the time of June 2012, there were a bunch of people that were disease-free. They hadn't made it into the barrel. But over those 5 years, there was a certain number of people that developed the disease. This here is where I like to think of it as risk. Again, the different names for risk could be attack rate or incident rate. I want to put them in there just because we see these terminologies. So that's our barrel. Now what doesn't happen in here, what we don't have just by looking at either one of these prevalence or the risk, we still don't really know how fast are new cases occurring. We can certainly talk about the attack rate or incidence rate in terms of who's at risk. What's the proportion of individuals who develop the disease, but it doesn't necessarily tell us how quickly is the drops of water from the spigot. And this is where there's some similarities with the Hebel-McCarter book and this sort of diagram, talking about as you're putting water into the flask. Well, now we want to ask ourselves the question, well, how fast are new cases occurring? Now, this is what I was taught to call as incidence. which does not help us when we have textbooks that say something else. So different people, it all is a matter of where they were taught and where, I don't know why there can't be common language. But also I have heard, and very commonly you hear this being referred to as being incidence density. And both the Hebel and our Hebel-McCarter pages that are scanned and our textbook do refer to this as incidence density. The only problem is our textbook also refers to this being incidence rate. So we're just going to stick to calling it incidence density. I'm okay with, again, I'm used to just referring to this as incidence, the way I was taught, but I'm okay with adding the word density. So this is our third measurement. It's talking about incidence density. And this is going to start telling us about the rate at which new cases are occurring. New cases or incident cases. And and I want to call it, I just want to abbreviate it this way. Now, the numerator for incidence density is very similar to the numerator of risk. It's basically the number of individuals who develop the disease, or the number of new cases, the number of incident cases. The denominator is what gets tricky. The denominator is reflected by the follow-up time disease-free, or I want to refer to it as the disease-free follow-up time. I think this is kind of the fun piece of calculating these values, and hopefully I can show you the fun that's to be had here. So at time equals 0, I'm going to bump up my game here a little bit. I'm going to say, let's say that we really had 1,000. We had our 1,000 individuals. I'm multiplying it up, so I have been using 100 to make your earlier pages of math easier. But I want to make sure I have enough folks to look at a 5-year. So let's say that, again, our disease is still skin cancer. And we had 10 individuals who had the disease at their baseline measurement. So 5 years go by. I'm now acknowledging the fact that I didn't really bother. This is now time is, now time is affecting my analysis, because if they had the disease, I didn't follow them. Now I'm thinking about how people are dropping out. And at time equal to 5, I had 990 individuals that I followed. I didn't follow all. I didn't actually follow the other 10. And let's say 5 years later, I now have 10 new cases. All right? So here's the fun part here, is from this particular 1,000 individuals, I had 990 that went forward, right? 980 remain disease-free. Right, because here at this particular point in time, at time equal to 5, I have 10 out of 990 990 individuals who were followed 5 years later. Out of that 90, 10 of them got the disease. So you see how I get my 990 and I split them out. So I have 10 new cases and 980 who still are disease-free even at time equals to 5. What I have to do when I think about incidence density is I need to give them credit. It's like, I like to think of it as store credit in a way. That, hey, the longer you stay disease-free, we're going to give you a little extra boost for it. So these 980 individuals, we need to give them person year. That's their credit. That's their store credit is person years. They get credit for all 5 years. So that means that each individual person gets 5 years. So 980 times 5 years, these 980 disease-free get to add or contribute 4,900 person years to my denominator. Well, the 10 individuals who got the disease, I don't want to give them 0 credit, because the thing is that some of these folks, maybe they got the disease within the first year or 2 after that baseline measurement. Some of them may have gotten the disease right there in year 4 going into year 5. Well, if I wasn't really following them, again, there's ways around there are some folks that will follow them every single year and you're tracking and you know exactly when they have the disease. But sometimes we don't. And one way that we can do it is say, well, if we averaged it out, John Doe may have had 4.5 years and Susie Smith may have had 2 years. But if we were to average all these 10 individuals, if we knew their exact time, on average, it would have been half that time. So one way that some statisticians will work at this is sort of this actuarial method. It says, well, let's give them half credit. So they get 2.5 years, or 5 years divided by 2, right? So they get half of the time, half of 5 years. So they get to contribute 25 person years. So these 10 individuals, they get at least partial credit. We don't know at what point they got the disease, but we can feel somewhat confident, make the assumption that on average, they get about half of the credit. Half of those 5 years, they get some credit towards the denominator. So when we calculate out the incidence density, we have the number of new cases over the disease-free follow-up time. I'm running close to the bottom here. Let me make sure I get those words in. So what I get is 10 over 4,925 person years. PY is sometimes how it's referred to. And if I've done my math correctly, we get 0.00203. And that's about, and there's different ways to display this. Sometimes you actually get that decimal place out, although that honestly, incidence densities tend to be very, very small numbers. When you're looking at the rate, especially for rare diseases, it's going to be really, really, really small. So it's a little bit, to leave that many decimal places out. So another way that this might be reported is to say it's 20 per 1,000 person years. Or another one is you might see 20 times 10 to the negative, right? Yeah, 1, 2, 3, yeah. Negative 4 person years. There's a couple different ways to describe this, and you might even still see something that will say 0. This 3 decimal places over to get the first digit. It's not too bad. There are some incidence density values that are so small that you're typically going to find, like, 20 to the 10 to the negative 12, because it's just so small. Sort of squeeze that in there. So these are 3 important measurements for us to look at the occurrence of the disease. It's the idea that maybe sometimes we just want to say, okay, right now, what's the information that we have? What's our proportion of individuals with the disease? If we are looking over time and we know that it potentially is affected by time, and we have to think about, well, how long did we follow them? This particular example here on this last page just happened to be, I made it even simpler by simply saying, oh, let's just say that, after the baseline, we had 990 individuals that got the disease. In reality, what we did 5 years later, we didn't really look at the 10 individuals who were prevalent cases at baseline. We really just looked at the 990. So we're clearly not following everybody for the same amount of time. What person years does, our denominator in this calculation, it allows us to take into consideration that people get followed for different amounts of time. So imagine, this is where it's helpful, if you actually do have a cohort and you're enrolling them at different times, and on top of that, if they have a particular event and they're no longer followed or they move away, so you know that the amount of time, their person years, is going to be different. Obviously, if you have 1,000 individuals, it can be somewhat tricky, but thanks to computers and technology, you can really plug in, this is when they started, this is when they ended, and you can actually calculate how long did you follow them. How many of those years that you followed them were they disease-free? Did they move away? Will they get credit at least for following them up to that point? They still were disease-free. Did they get the disease at a certain point in time? Then you can actually calculate their specific and not do this actuarial method. So this is just to help sort of give us a flavor. If we think about this picture up at the top, different ways to think about how is this disease accumulating over time. And then there's a whole idea, I think with the Hebel and McCarter pictures, they talk about what if you had a little trail that goes off, like there's a hole in our barrel, and we start talking about, and this is when we start thinking about mortality, if this is a disease that we're also triggering, well, how many then are coming out of this calculation? And that just adds another layer, but I really just wanted to touch base on these 3 major values that we talk about, whether you're talking about prevalence, incidence rate, or risk, like I like to call it, or this idea about incidence density. Again, tells us different pieces of information depending on if we're looking at just one point in time, or we start looking at between 2 time periods and comparing the 2 snapshots versus this last one here, when we start to recognize that different people have a different amount of disease-free time that they get to add to our denominator, and that's where this really cool calculation comes into. So I hope this was helpful, and again, this is just as for a reference point for you guys to come and visit.